as you know, I posted the last lab assignment on the Blackboard. Okay, so in the last lab assignment, last lab, so you are requested to design pipeline architecture, right? So and then actually I provide the single cycle processor design, so golden design of the single cycle processor design. So if you fail to complete the single cycle processor, but you can also you can uh, check uh, the how the single cycle processor is designed. Okay, and then based on this design, we can implement the five-stage pipeline architecture. Okay, so and then so, uh, so and then so you can find that the lab document actually include uh, much information, right? So which means that actually the lab document explains about um, the important design uh, principles. Okay, so actually for the pipelining architecture design, you need to add the pipeline registers. Also, uh, actually, the five-stage pipeline architecture includes the identity detection unit and data forwarding unit. And then also you can find that the data forwarding can be performed in the inside of a register file. And then this forwarding is called internal forwarding. But single cycle processor design, we don't require internal forwarding in the register file. It is because data forwarding is not necessary in the single cycle processor. But so in the pipeline architecture, so we require data forwarding to improve the performance, right? So internal forwarding needs to be implemented in the register file also. So and then, but fortunately, I provide the register file that supports the internal forwarding. But try to understand how the internal forwarding is implemented in the register file design. Okay. Then I'll briefly explain about the single five-stage pipeline architecture design. So so this is the single cycle processor, right? That's why I provide the golden design of the single cycle processor, right? And then based on the single cycle processor design, we can complete the five-stage pipeline architecture. How? You can just split the operation stages of this processor into five stages, right? Then we can insert pipeline registers between two stages, right? But uh, so but as I explained, so actually we need to check the timing of signals. Then I also explained the rule of this timing of signals, right? So for example, so we make the control signals delayed, right? So control signals need to go through the pipeline registers, right? If these control signals are used in the certain stage, right? Then the control signals need to have propagated via the pipeline registers, right? That's the rule. So we need to check the timing of signals. So it is very important and critical. So, so if the timing is mismatched, then your processor will generate the incorrect result. It means so you need to debug your processor design, but debugging, you know, but debugging will take long time usually. So in a software design, so debugging takes the long time, right? So it's the same to the hardware design. Implementation is it's a little simple, right? But debugging is more tricky. So it's more difficult than actually design, right? So try to check the timing of your signals. So I explained about the timing of the data write. The data write to register file, and then the write signal. So write the signal and destination register number, the write back stage, right? So we need to make the timing. We need to make the timing correct. So and then actually in the pipeline architecture design, you need to implement the pipeline registers. So the register is the group of if flip-flops. Okay, so you can add the instruction fetch slash ID pipeline register here, then ID slash x, then x slash mem, then mem slash write back. Okay, so we require 4 pipelining registers. Okay, so then also in the five-stage pipeline architecture design, so the branch unit is in the EX stage. So I explained the reason, right? So actually, our processor needs to support the 4 branch instructions, right? The PQPNE, BLT, and BGE. So actually, in order to implement the BLT and BGE, we require a subtractor, right? So we can implement the BQ and BNE using the equality check logic, but BLT and BGE require subtractor. So, so we assume that dedicated branch unit is in the EX stage. So it is separate from the ALU, right? So in a single cycle process design, we can use ALU for the branch instructions, but for this 5-stage pipeline architecture design, so we assume the dedicated branch unit is in the EX stage, and then actually this branch unit performs subtraction. Okay, and then we can make the required signals for branch instruction. And then, so because the branch unit is in the EX stage, if the branch is taken, then this processor will have 2 cycles of penalty. Then if the branch is not taken, then no penalty, because we assume that branch is not taken. Okay, so it's a prediction, it's a static prediction. Okay, so this is the example of a pipeline register. Okay, so I show the example of the instruction fetch slash ID, the instruction decoding pipeline register. So actually we can implement pipeline registers using the packed structure. The packed, it's called the packed structure in system Verilog. And then actually it's similar to the structure C or C++, right? So if you see this type, so you can find that, so we define a new type, a new structure, and then this is the packed structure, and then this structure includes the member variables. So you can find that this instruction fetch and ID pipeline register type includes two variables like program counter and instruction. Right. So in a five-stage pipeline architecture design, the PC needs to be propagated to the next stage. Also, the processor needs to propagate instruction into next stage, right? That's why the the instruction fetch and ID pipeline register includes the two member variables, the PC and instruction. So actually, this is the 64-bit register, right? 64-bit register, but we just split this register into the two parts, the PC and instruction, because these signals need to be propagated into the next stage, right? So this is the structure, right? Then the structure is defined, and then using this package structure, we can implement the pipeline register. I will show the example. Okay. So firstly, the package structure is defined, the system hello file, okay, and then I just declare the this structure variable. So, and then you can find that the this register the variable name is the ID. So why? So actually the we learned that in order to represent the pipeline register, so we just indicate the two stages like the instruction fetch slash ID. But and then also I define the package structure for this pipeline register as the instruction fetch the ID. But I just name the variable type the variable for this structure as ID. Right? So it is because after this pipeline register, the output of this pipeline register, these signals will be used. So the output of this pipeline register will be consumed in the ID stage, right? So we can say that these signals, the output of this pipeline register is the signals in ID stage. Do you understand? So for example, so this is the PC, right? This is the PC. And then we can say that, oh, this PC is the PC in instruction fetch stage, right? So we can say that this is the instruction fetch dot PC. Okay. You can represent this signal like this. But this PC, so this PC is propagated from the instruction fetch. It's propagated to the ID stage. Then what is this PC? This PC is the PC signal in the ID stage. So we can represent this is the ID dot PC. Okay. So output of this pipeline register. The output of this pipeline register is actually the signals in ID stage. So that's why I name this pipeline register is ID. So this it represents the pipeline register for instruction fetch slash ID. So type is the IF2 ID. And then you can find the behavior. The behavior of this instruction fetch slash ID pipeline register. It's a D flip-flop. Okay. So it's a, as you can see, we can implement the D flip-flop using arrays on the one FF. So then it's a synchronized with the clock signal. Then it is controlled by negative reset, asynchronous negative reset. So if the reset is given, so because this is the negative reset, so if the reset signal is 0, then it's initialized. Then this is the normal condition, right? So you can find that this pipeline register receives two control signals. So two control signals because sometimes we need to flush the signals. So which means that we need to make bubble, right? For what? So when does this pipeline register make bubble? Control hazard, right? So the branch instruction is taken, then we need to cancel the data, the signals in ID, right? So you need to make a bubble, right? So in this case, then this pipeline register receive flush signal. Then you can find that this is the instruction fetch of the one flushing. Then if this flush signal is given, then it's flushed. So all signals become 0. So we learned that in order to make a bubble, that we can make all control signals. All control signals 0, but we can also make all signals 0. Okay, and then sometimes the pipeline stages need to be stored. Which case? Data hazard, right? So load use hazard. If the load use hazard is detected, then the instructions need to be stored in the instruction fetch and ID stage, right? So you can find that if the stored, then the signals are not propagated. But I just implemented this operation like this. So if not stored, right, you can find that this is if not stored, and then the signals are propagated, right? So it means I do not define if store. So and then it is possible for the synchronous design because I do not define the case of if store is true, then it means that the ID.pc and ID.inst is not changing. So we don't need to define this case in the synchronous design. So that's why I just define the normal case. So if the story is not true, so it's a 0, then the signals are changing. It's a propagating. But if this pipeline register receives 2 signal, then the output is not changed, right? Because it's a story. So I do not define. And then, if you see that this statement, you can understand that, oh, if it's stored, then the output is not changing. So we don't need to define any behavior for if the story is true, right? So we can implement the pipeline register like this, okay? And then we can find that. So this is the ID.pt. the PC current. The current PC is propagated to the ID.PC. So this is the program counter signal in ID stage. Then also the instruction is propagated. Then I just define this is the ID that is. That's why I just named this pipeline register as ID. So and then it represents this is the instruction signal in ID stage. So this is the ID that inst. So like this way, so we can make the timing of signals next step. Okay, so in the ID stage will also generate the many control signals, and then we can also represent the control signals like this, like the EX dot ALU P or EX dot AL, so the regular select, something like that. So we can define the time. We can just indicate the timing of signals. Okay? So this is the design, and then so okay. The internal coding. The internal coding is implemented in the register file. So I also provide the register file, the complete design of the register file. So you don't need to modify any other design files. You can just modify the type of the CPU, the SB, right? The pipeline CPU design. Okay, and then I just provide the all modules, all complete modules. Okay, so inside, but you can find that the register file is changed. Okay, so because we require internal coding. So internal coding is defined like this. Okay, it's a RS1 E out. So this is the output port of the register file. Okay, so you can find that this is the RS1 is equal to RD, and if the register receives the regulate signal, then input is coded to the output, right? So this is the internal coding. So register receives the RD signal, and then this RD is equivalent to the RS. So RS1 is equivalent to the RD, or RS2 is equivalent to the RD. Then input is the updated value. So this value is to be coded to the output port. Right? This is the internal coding. So like the add x1, x2, x3, then this is in the write back stage, and then the ID stage, another instruction. So x5, x1, x4. Then we can find that the destination of this add instruction in write back stage is equivalent to the x1. X1 of this sub instruction, but this sub instruction is in the ID stage. So sub instruction needs to read operand from register file x1. Then the add is writing the new value to x1. So this is the RD in register file. And then the sub instruction is reading value from the register file. But you can find that this x1 is equivalent to this x1. Okay, the sub instruction needs to receive data from the former add instruction. So x1 is to be coding. So and then this coding is performed inside of the register file. So this is implemented in the register file. So you can find this additional line, additional part of the register file. So if the RS1 is a non-zero value, then RF data is are they are read from the register file, otherwise it's 0. So what does that mean? This is the X zeros, right? 0 register. Okay. So actually this part is to be included in the previous register file design, but I added this part. Then this part implements the internal coding in register file. Okay. And then the tricky part is in this parts in this wrap are data coding part and then hazard detection part, right? So pipelining is the concept of pipelining is simple, and then I believe you can use it to understand. But the data coding, and then hazard detection, hazard control. Hazard control is the tricky part. The tricky part is the pipeline design. So as you can see, data coding marks is is in front of the AAU input. Okay, so you need to implement the data coding from memory stage to EX staging, and then write back stage to EX. And then, as I mentioned, internal coding is already implemented, so you don't need to consider the internal coding. But in the pipeline architecture design, so you need to implement the data coding from memory stage to EX, so the early part of the EX. So this multiplexer, and then also the write back, the coding from write back to the EX stage. Okay, so you need to implement the coding multiplexers, and then you can find that the branch unit is located after the coding multiplexers. Okay, so the coding is supported in this pipeline design. And then hazard detection. So if the hazard is detected, like the data hazard is detected, then the instruction fetch and then ID stage is to be stored, right? So you need to also implement this operation. Okay. And actually, I just shows this design, right? So if the store signal is given to the is a pipeline register, then the pipeline register does not update the output value, right? So I already explained how this pipeline register works. The hazard case. But also you need to implement the pipeline store in instruction fetch stage. Okay, so this can be the tricky part. Okay, so I believe I give enough time for completing this last lab. So you need to submit the lab with your design by December 16th. December 16th, right? So, but please start early. As I mentioned, actually, you may take a longer time for debugging your design usually. Okay, so actually, design time can be the design maybe it's not difficult, but sometimes so if your processor generate the incorrect result, then you need to debug. You need to debug your design, and then it may take a long time. So please start early. Okay. Okay. So I explained about the lab assignment. Okay. Any question? No question. So, okay, so I will explain about the memory chapter, memory hierarchy chapter. Okay, and then so in the previous class we learned why the memory performance is critical, why memory performance is important for the performance of the entire computer system, and then also we learned about the memory hierarchy. So why do we use memory hierarchy? So it is because we cannot use perfect memory. Perfect memory means the memory size is very large, then memory is very fast, then also cheap. So this is the perfect memory, but we cannot use the perfect memory. So if the memory size is large and slow, then the memory is fast and the size is small. So the idea of memory hierarchy actually exploits the data locality. So which means that we can store frequently used data in the fast and small memory, right? But because the size is the small, we cannot store our entire data, right? So we just store frequently used data in the fast. So this is the concept of memory hierarchy. And then because of the memory hierarchy, then the processor firstly accesses the closure memory. The processor is here, right? So the processor firstly checks the register file, and then for the memory instruction, such as the load instruction or store instruction, a processor firstly accesses cache, right? Not real memory. Then cache is you can find the cache here. Then cache size is small, but it's much faster than the main memory RAM. Okay? So because the size is small, and it means that the request data can be found in the cache or not. Okay, and then I explained that if the data is found in the small memory, the cache, then it is a hit. And then if the data is not found, then this event is miss, right? And then we can define hit ratio and the miss ratio because we cannot find the request data. We cannot always find the request data. Okay, so we can define hit ratio as the number of hits divided by total number of accesses. Then so this hit rate ratio so will be can be larger than the zero, but hit rate hit ratio it is smaller than 1. Okay. So I also mentioned that if the hit ratio is high, then the performance can be improved. Usually improved, not always. Okay. So this is the idea of memory hierarchy. Then also this is the important. You need to understand the two types of locality, the data locality. So we learned about the temporal locality and spatial locality, right? And then because of this locality, we can apply memory hierarchy action. So, so let's learn about the memory technology, the briefly. Okay. So what is the memory? So memory is just a device that can store data, right? And then actually we can understand the memory as the array. Okay. So actually we already implement the memory components such as the register file or instruction memory or data memory, right? So when we design a memory module, then this memory module receives the address, right? And then the memory has the multiple element. Then this element is indexed by address. So if you see the memory module, then you can find that, oh, this is the data. Then we just declare an array of data, right? In the memory module, the system variable module. And then you can find that in order to access a certain element of data, then we can use the address as the index of data. Then we can read a certain element in the memory. So this is the conceptual view of the memory. Then we can define the number of elements. Number of elements is the depth. Okay, and then number of bits. Number of bits per element is defined as the bit. Then what is the size of this memory? Obviously, so this memory can store bit multiplied by depth bit, right? So this memory can store this amount of bit data, right? But we frequently use byte data, not bit. So we can represent the width as the byte. Okay? So using this equation, we can calculate the size of memory. Okay. So for example, this memory has the 4 byte of width. Okay. It is 32 bit. And then this memory includes the 128 entries, right? Elements. So what is the size of this memory? So 128 multiplied by 4, so this is the 1512 byte, right? So this is size of memory. Okay. So this is also example, and then we can just give address to the memory, and we can test the element of the memory. But real memory can be implemented like this. So this is the basic structure of the physical memory. Okay, so I mentioned that we can store bit data. We can store bit data inside of the memory. Then actually most memory device has this structure. So the bit data is stored in this part, and then this part is called the memory cell. Okay. So we can store bit data in the memory cell. So then you can find that this memory cell is connected to the word line and bit line. Okay. The two lines are connected to the memory cell. The word line is used for activating or deactivating this memory cell. So what does that mean? Activating means, we can access. Access means read or write to this memory cell. So The activation or deactivation is controlled by this word line. So for example, if this word line is 1, then we can access. We can access this memory cell using bit line. So in order to read or write certain data to this memory cell, then we require the wire, right? The wire for accessing this memory cell. So using the bit line, the data can be read or data can be stored to this memory cell. So bit line is the this is the wire that can read or write a bit data to the memory cell. And then word line is the control line. So we can activate or we can deactivate the target memory cell. So this is the conceptual view. So it's a word line is 1, then stored bit is 0. Then what is this pin 9? The pin 9 is 0 because this is the activated. So we can read this value. And then this word line is 1, and then the stored pin is 1, the pin 9 is 1. So we can just, so this pin 9 is connected to this memory cell. So the data, the value of the pin 9 becomes equal to the value stored in the memory. But if the word line is 0, then pin 9 is not connected to this memory cell. Okay, you can understand the memory structure like this. And then, as I mentioned, most memory devices have the same structure. So actually, we learned about some different types of memory, such as the SRAM, DRAM, or magnetic disk is different. Okay, the SRAM, DRAM, and flash memory. Okay, the solid state memory. So these, the SRAM, DRAM, and flash memory are called the solid state memory. This is because this memory is we can implement this memory using the semiconductor technology, right? But magnetic disk is a little bit different. So it's a kind of a mechanical device. But the solid state memory devices can be implemented like this. Most solid state memory devices have the structure like this. The memory cell, there is a memory cell, and this memory cell is controlled by word line, and pin 9 is connected to this memory cell. Okay, this is the entire view of the memory. Okay, so you can find the decoder here. Then address is given to the decoder, right? And then because this address has the 2-bit data, and then using this decoder, we can generate the 4 word lines, right? So, and then memory cells are connected to the word line horizontally. So, this word line can control the multiple memory cells, right? So in this example, in a single word line, 3 memory cells are connected. So using this word line, we can control the connected memory cells. These 3 connected memory cells. Okay. And because there are 3 memory cells are connected to one word line, so we require 3-bit pin lines. Okay. So pin lines are also connected to this memory cell. So as I mentioned, the memory can be structured as the array, the 2D array. So word line can activate the entire entry, like entire element. Then the multiple bit data can be stored in this entry. Okay. So address is 2-bit. Using the 2-bit address, we can generate the 4 word line. And then in each word line, 3 memory cells are connected. So in line, there are 3-bit lines. So this is the width of the memory. The width of the memory is the 3 bit. And then what is the depth? Depth is the 4. So this memory can store the 4 multiplied by 3. The 12-bit data can be stored. So it means, and then we can just calculate the depth of the memory using the number of bits in the address. Right? So for example, we can use the 8-bit address. Right? Then using the 8-bit address, we can make the 2 to the power of 8 word line. Right? What is this? This is the 256. And then we can just change the bit width. The width of this memory. So let us suppose that the bit is the 8-bit. So which means that the width is the 1 byte. Then what is the total size? We using the 8-bit address. Then the total size of this memory is the 256 multiplied by 1 byte. Okay, so 8-bit. So this is the 256 byte. Do you understand? So the pin numbers in address can determine the depth of the memory. Okay, we can calculate the maximum memory size like this. Okay, so this is the maximum size of the 8-bit address. So that's why, so for example, so your in a 32-bit computer system, the address has the 32-bit, right? So that's why this address bit determines the maximum size of this 32-bit computer. The maximum size is the 4 GB. Okay, so so this is the basic knowledge on memory. And then, so this is the SRAM. So I mentioned that all memory devices has this structure, the word line and bit line. The SRAM, we can implement the SRAM like this. So if you took this the logic design, and I believe you understand the behavior of transistor. Then actually the word line is connected to this MOS transistor. The word line just control the connection of this bit line. And actually the data is stored at this closely coupled inverters. Okay? This is the SRAM cell. So data is stored in this closely coupled inverters. And then actually the type of this memory cell, determines the performance of memory. Okay. So because the SRAM uses the cross-coupled inverters. SRAM is best because this is the active device. So we can just actively boost the voltage level of this cross-coupled inverters. So that's why the SRAM is very fast. But then also we can implement the SRAM using the normal processor technology. Normal process technology is that. So we can implement the CPU, right, using the processor technology or logic technology. And then I mentioned that CPU is very fast compared to the memory. So it means that the performance of logic technology, semiconductor technology is very fast. And then SRAM, and we can implement the SRAM using the same technology, same CPU, semiconductor technology, same logic technology. So SRAM is very fast. So SRAM can be included in the same CPU chip, same CPU die. Okay, so that's why cache, you know, when you read the CPU specification, you can find that cache is inside of the CPU, right? Because caches are implemented using SRAM. And then we can apply the same technology, same semiconductor technology to the cache. So caches can be included in the inside of the CPU chip. So it means the caches are also very fast, but it is included in the CPU chip, inside of the CPU chip. So, okay. And then how about the DRAM? The DRAM is different. So this is the NMOS transistor, and then actually the bit data of DRAM is stored in the capacitor. This is the capacitor. So capacitor is a passive device, right? Then actually it's slow. So in order to charge or discharge electrons in the capacitor, it will take time, right? But this time is slower than the cross-coupled inverters. That's why DRAM is slow. And then also, in order to implement this capacitor, then we need to use the somewhat different semiconductor technology, semiconductor process. Okay? So that's why DRAM is outside of CPU, right? And then also DRAM is called the external memory because it's outside of CPU. Okay? So it is because it's not easy to apply the same technology, same semiconductor process to the DRAM. Okay? So DRAM is the off-chip. So it means that we can just the DRAM is the external memory, the outside of the CPU. That's why DRAM is slow. So because of this property, DRAM is also slow. So in this slide, I just compare the SRAM and DRAM. So it is because we use the SRAM for the register file and caches. DRAM is the main memory. First is the SRAM is mentioned. The SRAM is expensive. The DRAM is less expensive. Latency is low. Then DRAM is high. Which means that the SRAM is best. You can also compare the density and capacity. Volatile. The volatile means that if we just turn off the power of the memory, then the data is just erased. It's called the volatile. Then the SRAM is SRAM and DRAM are both volatile. Okay, but so you can find the reference here. It's kind of deeper level, but you can find that no need to refresh code. And then DRAM requires refresh. Then refresh also take time. Okay, placement is internal and external, as I explained. So we can apply a different memory technology, the different types of memory device, and then actually different type of memories are used for different levels memory hierarchy, right? So as you can see, the different memory types has diverse characteristics, right? So we can implement the memory hierarchy using different memory types. So this is the internal, then you can use the SRAM. This is the external, then for the main memory we use the DRAM. Then for the storage we can use flash memory or magnetic disk. Okay. So this is the basic knowledge on the memory devices. And then actually the DRAM. So DRAM is a kind of a very complex system. So which means that so I said that this is the basic structure of the memory devices, but because of the unique characteristics of DRAM, actually the DRAM requires the more complex logic, more complex control logic. So I will explain the detailed logic here. Okay? But again, actually we need to control the DRAM. So actually the DRAM is controlled by memory controller. Okay. But okay, so you can find the different. And then currently we use the DDR, the double data rate. So it means we can use the rising edge and then falling edge of the DRAM clock for accessing DRAM data. And then actually the GPU uses the QDR. And you know the GDDR. So we use GDDR for the GPU DRAM. And actually the GPU DRAM implements the QDR. Okay. So this this slide shows the technology advanced in the DRAM technology. You can find that the capacity is increased, the cost is reduced. Right? It represents the cost per gigabyte. Right? Then, so I will explain this, but I hope you can understand this one. So the problem is RAM is slow. Right. The CPU is fast, RAM slow. And then also another problem is that the CPU is here and DRAM is outside of the CPU. And then we just connect the CPU and then DRAM using the metal wires, the PCB, right? PCB board, the printed board. So, and then actually this bandwidth the bandwidth between CPU and DRAM is limited by these external wires. So when we organize the computer system, we need to also consider the technology, the real technologies and cost. So that's why, uh, why, why do I explain this? Because actually, in order to connect the CPU and RAM, we need to make the pin, right? So then if you buy a CPU, and if you just uh, check some CPU chip, you can find that the CPU chip has many pins. The pin is the interface to the outside world, right? But pins are very expensive. So pins are limited resource. Okay, so actually enough to make a pin, the pin also uh, take up some area, right? So we cannot use many pins. Okay, so the bandwidth is limited. Okay, so actually in order to increase the performance, so the DRAM is very slow, but we want to improve the performance of DRAM. Then a possible way to improve the performance is to increase this bit width. So it means, this is the array, the memory, and then the memory is controlled by word line and then bit line, right? And then if we increase this bit lines, number of bit lines, then with the one memory access, we can read more data. So by doing this, we can increase the performance of memory system, right? And then actually this pin 9 determines the bandwidth, bandwidth of the memory system, right? So you can understand that now to improve the performance of a memory, we can increase the pin 9, okay, simply. But this is not reasonable approach to the CPU and RAM, right? Because of this limitation. Okay? You cannot use the wide bus. But we want to. So actually, this is our choice. Using the narrow channel, using the low bandwidth channel, then we can access the DRAM. But problem is that our DRAM is also slow. So in order to read the certain amount of data, it will take very long time, right? Because the DRAM is slow. So we want to read this amount of data, right? This amount of data. So in order to read this amount of data, it will take very long time, right? And then in order to reduce this time, so this is the time, then we can just increase the number of bin lines, but it's not with it's and then the cost matters, okay? Because of the cost, so it's not the realistic approach. And what is the possible solution? So in the real world, think about the real world. So you need to collect a certain data from the different person, different friends, and then actually this friend is very slow. Okay, worker is very slow. Then how can we increase the performance of this other part, other workers? We need to receive a certain data from the other workers, but this worker is very slow. this case, we can apply parallel processing, right? If there are more workers, and then if more workers can work in parallel, then we can increase the performance. So we can receive more data from the more workers. We can apply the same approach to the RAM or memory. So in this figure, you can find that there are multiple memory partitions. So you can find and then this partition is called a bank. So and then you know the bus is narrow. So we can control multiple memory partitions or multiple banks like this. We can give address to the bank 0, and then it will take time, right? So address 0, and then we need to wait this amount of time. Then we can give another address to another bank, right? Then we will wait this amount of time. Then so we can also give another address to another bank. Okay, so then actually if there is only one bank, one memory partition, then the latency looks like this. So there is a single partition. Then address is given. Oh, DRAM is so slow. After some time, you can get data. Okay, this is the latency of DRAM. But if we just use the multiple bank, then this is the address for bank 0. This is the address for bank 1. And then it will take the same time. The latency is the same. The data can be read out. But after that, can read the data for this address 1. If we just give the different address to the different banks, then we can get the data, more data, the same time window. So now to improve the performance of slow memory, we can the memory can include the many banks, the multiple banks. Okay, then by doing this, we can improve the performance. Actually, the DRAM employs this multi-bank structure, okay, enough to improve the performance. And then this is called the bank level parallelism. Okay. Okay. So this is the some technique for the DRAM. And then flash. Then recently we frequently use flash memory as we frequently use the SSD. SSD represents the solid state drive, right? SSD. So it means, and then we use SSD as the storage device. So it means that the SSD is the non-volatile memory, which means that the data is maintained even though the power is off. Okay? And then for the SSD, we use the flash memory. Flash memory is the storage memory, storage medium. And then, if we use the SSD, then performance is also improved. Performance of the computer system is also improved because the flash memory is much faster than the magnetic disk. Okay, so you can find that it's 100 to 1,000 times faster than disk. Okay, but it's slower than RAM. So, okay, so around 1,000 times slower than RAM, but it's much faster than magnetic disk. Okay, that's why we use the flash memory as the storage media of SSD. But it's more expensive, obviously. It's more expensive than the HDD. Okay? Then, as I mentioned, we can also use the hard disk drive. The hard disk drive looks like this. So inside of a hard disk drive, so there are multiple letters, like letter. Then the data is stored on the surface of a planet. Okay, so you can find the multiple planets here. Then actually data is stored in the surface of a planet. Then using this arm, head of the arm. So actually, as I mentioned, the hard disk drive is the mechanical device. So we need to make the planet rotate. Then actually using this arm and head of this hard disk drive, we need to locate the location of data. So because this is the mechanical process, the hard disk is very, very slow. Okay, so you need to understand why hard disk is slow. But flash memory is the solid state memory. So flash can be controlled by electric signals. That's why flash is fast. Actually, flash means it's the best. The flashy DC Marvel, DC Comics, right? It means it's the best, right? It's the same, right? Actually, you know, you know. So, the access time of the hard disk drive is right, the millisecond access time, much slow. Okay, this is the hard disk. Okay, so I'll stop here, and then in the next class, I will explain about the cache. So this is also very important part. Okay, so try to end the class. Thanks for attention.